Welcome. This is an additional video designed to give us a little bit more practice with dynamic programming, because if you just work the neoclassical growth model out over and over and over, that's kind of cool. Maybe it means you'll get a good idea of how to do the dynamic programming, but then again, maybe not, because maybe you're just kind of like memorizing the steps for the neoclassical growth model and you're not really getting the full picture. Now, maybe that is you. Maybe it's not you. Maybe you get this immediately and you're like, hey, cool, this is super easy. And you don't need to watch this. In which case, hey, this is not a required video here. This is just a little extra practice if you think you need it. Okay, so a little bit of recap here. You get your problem, right? You get your U of CT and your constraint and all that stuff. You're always going to have a Bellman equation that looks something like what you see in equation 1. V of kt equals a natural log of ct plus beta times v of kt plus 1. And then ct is going to be set equal to that resource constraint with all the endogenous variables substituted into it. Now, you could have more in the utility function. You could have, say, money in the utility function. If you've taken my money and banking course, you'll actually have seen something with money in the utility function, and you'll even learn a little bit about why money could be in the utility function. There's actually a whole article from Milton Friedman about why having some real money balances as your holdings would be kind of a good thing, right? Because you have a little bit of money in like a savings account, which, save it for a rainy day. Hey, good stuff. So you could have something like, say U of CT and MT, where MT is money, which is equal to the natural log of CT plus gamma times the natural log of MT, right? If that's the case, right, you've got two inputs in your utility function. You only substitute CT in. You still leave MT alone. So regardless of how many terms you have in your utility function, you're only substituting stuff in for C sub t. Now, the constraint might be longer as well. You could have, say, money and bonds in there, in which case you don't just have the flow of capital, which is investment, right? You'd also have the flow of bonds and the flow of money. So this stuff right here, 1 over 1 plus the real interest rate times BT plus 1, well, that's the discounted present value of tomorrow's bond holdings plus today's bond holdings minus the discounted present value of tomorrow's money holdings and today's money holdings. Now, you have 1 over 1 plus the real interest rate for BT plus 1, right? Well, that's the discounted present value of tomorrow's bonds. It's telling me what tomorrow's bond holdings, weighted by the return or the expected return, would be worth to me today. Money, that 1 plus the inflation rate times MT plus 1, well, that's the discounted present value of tomorrow's money holdings. What's that worth to me today? Well, you got to control for the effects of inflation with money because, well, yeah. So in order to control for the effects of inflation, you got 1 plus the inflation rate, 1 plus pi t. Now, in this case, the Bellman equation would be V of kt, bt, and mt, because you've got 3 arguments in there instead of just 1. And that's equal to the natural log of consumption plus gamma times the natural log of MT plus beta times V of KT plus 1, BT plus 1, and MT plus 1. So you take 2 more derivatives for your first order conditions, and then you take 2 additional derivatives in order to get the partial of V of KT plus 1, BT plus 1, MT plus 1, all that stuff, right? So you have 6 derivatives total here as opposed to 2 derivatives in equation 1, but the process is still the same for each derivative. Skipped over a lot of stuff here. Okay, so your Bellman equation, like I said, is always going to look something like V of kt equals the natural log of ct plus beta times V of kt plus 1. Constraint's always going to be ct equals stuff, and you can either substitute that stuff in for ct or you can keep it in there. Either one works since it's really the same. It's just if you keep ct in there, right, you don't put the stuff in there, you need to multiply that derivative, that 1 over ct, by the derivative of the constraint with respect to whatever that other variable is, right? So if it's capital, well, it'd be 1 over ct times negative 1. If it was, say, bonds, it would be 1 over ct times negative 1 plus the real interest rate to the negative 1 power. Why is that? Well, it's right here. So if you're like, okay, well, what the hell? Don't worry about that just yet, because we will be getting to it. So once you have your Bellman equation, right, and you get that derivative, that first order condition, Remember, you're going to have that partial v of kt plus 1 with respect to kt plus 1. You're going to need to know what that is. But if you look at the left-hand side of this, well, you've got kt and kt plus 1, but these subscripts don't align. There's nothing you can do to make this derivative have the subscripts align properly. You need another derivative. You need to take the partial of v of kt with respect to kt, not kt plus 1. And then you update that one time period. Now, when you get that derivative, the time subscripts will match up. So you'd have v of kt, or what, I guess dv of kt, dkt. And, well, yeah, there you go. That would match up. And then you need to update everything by one period. So you'd have dv of kt plus 1, dkt plus 1, and plug that into what you get right here. And then you'd move that 1 over ct to the other side, and blammo, you have your Euler equation for capital. So let's do an example. Say you got the utility that you've seen from the neoclassical growth model. So it's beta to the t times the natural log of ct. And the constraint with capital and now bond holdings is c equals at times kt to the alpha minus kt plus 1 plus 1 minus delta kt. That's output minus capital investment, right? But then we're subtracting 1 plus the real interest rate to the negative 1 times bt plus 1, and we're adding bt. So we're adding in the flow of bonds now. So it's not just the flow of capital, it's also the flow of bonds. Now in that case, we're choosing capital and we're choosing bonds. So our Bellman equation is going to be v of kt and bt equals the natural log of ct, right? Because the utility function is unchanged. It's just the constraint that's changed. So it's going to be plus beta times v of kt plus 1 and bt plus 1, because now we choose between investing and holding bonds, which means we invest less, right? Because you're going to have the same income, the same output. It's just less goes towards investment, more goes towards, say, holding bonds. So bonds would work the same way as capital, right? You chose b sub t yesterday, and you can choose b sub t plus 1 today. So you formulate your Bellman equation, where you just take that constraint and substitute it in for c sub t. So this equation 4 and equation 3 are identical, right? It's just you took that constraint and put that in for c sub t to give you equation 4. And now you need to get two first-order conditions, one for capital and then one for bonds. So the one for capital is negative 1 over ct plus beta times dv kt plus 1 bt plus 1 with respect to kt plus 1. And you set that equal to 0. Right? So remember, for your first order condition, you set that equal to 0. It's the first derivative set equal to 0. For bonds, this one's a little different, right? It's negative 1 plus the real interest rate to the negative 1 power over ct plus beta times the partial of v of kt plus 1 and bt plus 1 with respect to bt plus 1. Now, why is it this? Well, if you look at your Bellman equation, you take the derivative of the inside. So the derivative of the outside is 1 over ct, right? Times the derivative of the inside. What's the inside? Well, the derivative of the inside is, let's see. Is it going to let me? Okay, well, it's this minus 1 plus r to the negative 1. That's what the derivative of the inside would be. So it's minus 1 plus r to the negative 1. And that is plus partial v of kt plus 1 bt plus 1 with respect to bt plus 1. Okay, so I hope that's not too bad. Now what do we need to do? Well, I don't know what this guy is, and I don't know what this guy is. So how do I get those? Well, I need to go back to my Bellman equation. So I got to go back to equation 4, and I have to take the derivative of v of kt and bt with respect to kt and update it one period, which gives me this. And then I need the derivative of v of kt and bt with respect to bt, update it one period, and that gives me this. Okay, hopefully that's not too bad. Seems like, a lot of math, but the steps are really the same. So the more you do the steps, the less math it really seems like you're doing. Now, equivalently, we could just write this as, say, equation 7 and equation 8. So it's negative 1 over ct plus beta times partial v of kt plus 1 and bt plus 1 with respect to kt plus 1 for capital. And for bonds, it's 1 over ct times 1 plus the real interest rate of the negative 1 times negative 1 plus beta times partial v of kt plus 1 and bt plus 1 with respect to bt plus 1. These guys are set equal to 0. Okay, so now we got to do the other two derivatives, update in one period, and that will give me this guy and this guy. All right, so I need these guys. What do? Well, I take the derivative, start with capital, take the derivative of v with respect to kt, and that gives me the now infamous 1 over ct times the marginal product of capital less depreciation. Now, if you're like, wait a minute, isn't that the same as what we saw with the neoclassical growth model? The answer would be yes. Why is that? Well, there's an economic reason and a mathematical reason. The mathematical reason is, if you look at this, right, this is our constraint substituted in for CT. The constraint's linear. The constraint's additively separable. So if it's additively separable, the more crap you put in that constraint, as long as it's being added in, when you take that derivative, it all differentiates to 0. So if you got bonds here, right, you take the derivative across this with respect to kt, well, that's not a kt, and this isn't a kt, so all this crap in purple here differentiates to 0. So the derivative would be unaffected with the more terms you add into it, because it's additively separable. Okay, that's the mathematical reason. What's the economic reason? Well, the economic reason is potentially even easier than that. And that's because at the margin, right? Because remember, you're always like, hey, at the margin, we make these decisions at the margin. What does at the margin really mean? At the margin, well, I guess mathematically means partial derivative. But at the margin, when you're making your decisions for capital, it's independent of bond holdings. It's just with respect to capital. What's going on with capital? We want to look at just that. So at the margin, economically speaking, we're only looking at this with respect to capital. So that is unchanged. It's not going to be any different. No matter how much more crap you have in that constraint, the marginal product of capital will always be the same, unless you change the functional form for the production function. So if you update this one period, you get your derivative of v with respect to kt plus 1 equals 1 over ct plus 1 times your marginal product of capital, and t plus 1 is at period t, less depreciation, and depreciation is constant. Cool. We've seen this, right? We saw this with the neoclassical growth model. All right, well, I take the right-hand side of equation 9 here, and I plug it into what we had in equation 7. What was equation 7? This was equation 7. So I plug it into that derivative for equation 7, and that gives me this. Move that 1 over ct to the other side, and I get 1 over ct equals beta times 1 over ct plus 1 times marginal product of capital less depreciation. Now we're going to hold on to equation 11 for just a couple of minutes, because now we got to do the same thing, but we got to do it for bonds. So I need the derivative of v with respect to bt plus 1. What do? Well, I take the derivative of v of kt and bt with respect to bt, and what do I get? Well, I get 1 over ct. Why do I get 1 over ct? Well, let's go back to our Bellman equation again and take a look. Okay, so the natural log of all this stuff is all consumption, right? So the derivative of this is 1 over ct times the derivative of the inside. What's the derivative of the inside? Well, this isn't a bt, so this differentiates to 0. This isn't bt, this differentiates to 0. This isn't bt, this differentiates to 0. bt plus 1, close. But as in the Clinton administration, no cigar. So that differentiates to 0. So all we have is just this lonely bt. And the leading coefficient in front of it is 1. And its exponent is 1. So the derivative of bt is 1. So via the chain rule, that tells me it's just 1 over ct. update that one period, it's 1 over CT plus 1. That derivative is like ridiculously easy, isn't it? Yeah, it's a lot easier than what we had with the capital stuff. Cool. Well, I'm just going to take the right-hand side of equation 12 and plug it into, I believe it was what, like equation 8? I hope it's equation 8. Yeah, equation 8. And bada bing, bada boom. I move that 1 over CT times 1 plus the real interest rate to the negative 1 to the other side, multiply both sides by 1 plus the real interest rate, and that gives me equation 15. 1 over CT equals beta times 1 over CT plus 1 times 1 plus the real interest rate. Cool. We've actually seen this one before. We saw this in chapter 5. This was the Euler equation when we had exogenous income, right, where it was just sort of endowed upon us. Now, if you're like, hey, that's where the similarities end. Not really. In the next video, which, well, you'll see why there's a next video coming up towards the end of this slide, or end of this video, where I give you guys a problem to solve out. In the next video, I'm going to solve it out for you, give you guys the answers. And then I'm going to make a comparison. I'm going to show you that in equilibrium, equation 15, right, that Euler equation for bonds would actually be the same thing as equation 16, which is the Euler equation for capital. Now, if you want to be a little dangerous, try figuring it out for yourself. Figure out why. It takes just a little bit of manipulation inside the parentheses in equation 16. But if you can get equation 16 in the form of 1 plus a bunch of other stuff, and then look at equation 17 and go, okay, well, consumption is the same here. Beta is the same. CT is the same. CT plus 1 is the same. So the only thing that's different is what's in those parentheses. But, right, it's all kind of got to be equal in a general equilibrium context. So if that's the case, 1 plus that real interest rate should probably be equal to what's in the pink in equation 16. So get what's in equation 16 in the parentheses into a form of 1 plus other stuff, and then take a look and see if that other stuff, what that is, and then try to reason in your head why that would be equal to the real interest rate on bonds. Again, might take a little bit of time, a little bit of extra thinking. This isn't the easiest stuff in the world, but just think about it and then go, all right, well, if it's a general equilibrium context, maybe there's a reason for this. But we'll spend more time with that in the next video. So let's talk about a couple things here. For each variable in your function v, you'll have 2 derivatives. The first derivative is the first order condition, where you just take that derivative, set it equal to 0. It's going to be something like partial v of kt and bt with respect to kt plus 1. And it's always going to have mismatched time subscripts. But you're going to need that derivative on the right-hand side of that first order condition with the matching time subscripts. You're going to need to know what that is. So then you go back to your Bellman equation. You take the derivative of v of kt and bt with respect to kt, and you update the time subscripts of that derivative. This now has matching time subscripts, just like what you needed in that first order condition, and you plug that into your first order condition. And the Euler equation will give you the optimal time path for whichever variable you're looking at, right? If we're doing it for capital, it's going to tell you the optimal time path for capital, and then how your consumption savings decisions based on your capital, like your optimal capital time path, would be governing your optimal flow of consumption with respect to capital, right? Same thing for bonds. It's going to tell us how we need to use our resources each period. And it's giving us an intertemporal link between today and tomorrow. If I choose to do X with my capital today, right, what does that mean for tomorrow? What are the implications of that for tomorrow? If I make a decision today, if I want to spend a bunch of money today, will I be able to pay my bills tomorrow? Right? That's kind of what the Euler equation is telling us. It's a bastardized, simplified version of it, but that's basically what it's saying. It's telling us how to use our resources each period and the implications of how we use our resources today for next period. So you're going to want to practice this stuff, right? It will become second nature. And the idea is that we're going to use the Bellman equation to give us the Euler equations that we need for the model. And the Euler equations tell us the optimal intertemporal flow of resources for the agent through various instruments, whether it's capital, bonds, money, things like that. So the equations are really telling us how the household is behaving optimally. Now, here's what I want you guys to work on your own. You're going to have the utility that you've seen from the neoclassical growth model. So it's just the natural log of consumption. And you've got the constraint with capital, bonds, and money, and pi t is inflation. So with this constraint right here, in this utility function, first I want you to tell me what the Bellman equation would be without consumption in there, right? With all this stuff in there instead. And then you're going to need to take some derivatives. How many derivatives total? 6. You'll have 3 first-order conditions, and then 3 derivatives of v of kt, bt, and mt with respect to kt, bt, and mt, updated one period, and then plugged in. So try to do it all on your own. See if you can get the Euler equation for money, because here's a little spoiler, right? Remember when I walked you through and I said, hey, even if you've got bonds in the constraint, the Euler equation for capital is going to be the same. I remember saying that pretty clearly, actually. So if the Euler equation for capital is the same when you put bonds in there, it's probably going to be the same when you put money in there. But we can extend that one step further. Not only will the Euler equation for capital be the same with money in there and bonds, the Euler equation for bonds will be the same with money put in there. So really, yeah, you do have to take the derivatives of that, but you don't really, because you kind of already know what they are. Just make sure that the arguments in your v functions are updated to include money. So really, the only one that you don't know that you haven't seen yet is the derivative of v of kt, bt, and mt with respect to mt plus 1. So you're choosing kt plus 1, bt plus 1, and mt plus 1. Happy hunting. If you need help while you're solving this stuff out, please email me. I'm happy to help. I'm happy to work with you. I'd really rather not give you the answers, at least right now. I want to let you work towards the answers. And in a couple of days, the answers to this problem will be posted on YouTube and iLearn for you to watch. And you can go like, hey, let me gauge this against what I did. Does this work? Does this not work? Did I do it right? Did I do it wrong? And we can go from there. So thank you for watching. Be on the lookout. There's another video coming on Tuesday where we start a new model. And then I think I'll probably post the answers to this on either Wednesday or Thursday. Probably Thursday. Give you guys a couple of days to work on it. And you have the homework due on Wednesday. Yeah, so I'll post it Thursday. But yeah, thanks for watching. I hope this helped. And if you have any questions, message me. I'm here to help. That's my job as your teacher. So thanks for watching. Bye.